Welcome to another episode of Mechanisms and Mentorship. Another special guest today, Aaron Robinson. He has 20 years plus of experience in device industries across all phases of R&D and roles such as NPD Technical Project Manager, Startup Co-Founder, and Engineer. He has a sound business and technical acumen to build teams and momentum to solve complex problems. Aaron excels at growing people, products, machine design, material research, and manufacturing processes. 6 of 10 products he's developed have been or will be commercialized, and all of them have produced invaluable learning. Aaron, welcome to the podcast.
Thanks, Raf. It's good to be here.
Thank you. Well, one of those 10 products is going to be this one that we have in front of us, right?
That's right. This might even be 7th of 11th. I'm not sure. I have to recount.
All right. So if you want to pull on the handle so people can see, because it's hard to see with the contrast, what is this that we're looking at in 30 seconds, Aaron?
This is called a threaded insert installer. They exist in different forms in industry, but it's really used to put brass or metal inserts that have threads in them into a thermoplastic part, usually 3D printed or injection molded. And so it's really kind of a heated arbor press is the way to think about it.
All right, and we have the CAD model for this that Aaron designed as part of the team, and I also helped with this project, so I'm very excited to show you. So this is the CAD model. If you want to do like a quick spin so people can see the contrast, that's the CAD model for this. Now we're going to do a quick demo to show you how this works, and then we'll dive into Aaron and the whole logic behind designing this product. All right, so now Aaron's going to show us what this is and what problem it solves.
Sure. So a lot of times, if you 3D print or injection mold a part, they're not great for putting strong threads in, and so it's common in the industry to press a threaded insert inside of it. So one might look like this. So it's got some sort of knurled surface on the outside that grabs the material, but you normally have to heat these up and then press it in, and it melts the plastic, and then you have a good threaded insert to put a screw into. And right now in industry, there's either some DIY solutions, like a lot of times people just take a soldering iron and press those inserts into the hole, or there's some, you can find on YouTube and all over the place, you can find different examples where people have printed their own version where it holds a soldering iron and presses it in, or you can buy ones that are more industrial for thousands and thousands and thousands of dollars. So the idea behind this one is sort of be a middle of the road, not really a DIY solution, but at the same time not one that cost $5,000, $10,000 or more.
So basically, you need to do it at home for $100, you can buy a car with the money.
Yeah,
but this is like the solution in the middle.
Exactly.
All right.
You got it.
So what's the problem, though, that we're trying to solve with this?
The problem is, how do you get good threads into a plastic part consistently?
And what seems to be the main issue?
A lot of times in industry, if you're just using a soldering iron, the tip isn't designed for the threaded insert, and so we change these tips out for different threads, and that's been known for quite a while. But we also have made this one so that you can quickly and easily change the tips. There's some other tools that we're working on. Raf's working on that right now on how to do this without turning this off. All the ones that we know of, you have to let it cool down, then grab it, then change the tips if you want to do different parts. Or if you're using a soldering iron, the other problem is it's really hard to get them in straight and consistently. The soldering iron might be too hot, or it just goes off kilter and you don't have a straight hole anymore.
Yeah, so basically what I've seen is the main problem is when you use the soldering iron and you melt it in, if you will. This is a 3D printed part. Maybe it'll be angled. It's not going to be totally perpendicular to the surface. And that's a big issue because when you come in with your screw, you want it to be perfectly perpendicular to the surface. Is that right?
You got it. That's it. Okay, so let's say we want to change tips. Really, we've just got sort of a helix, a quarter-turn helix in there. And right now, we've been using this tool to store them and to remove them. We might change that, but here you can remove one tip. You can see it's tricky to kind of grab it, so we're working on that. And then you put another tip in there. So you never have to touch it, and you can swap tips out while not getting burned. And then you'd go and you'd have your heated insert, press down on it, and push it into the plastic.
So like anyone knows, in product development, there are several iterations to a product. You have to test and validate it. So now Robinson is going to walk us through some of the evolution of this. This is more of the ancient one. This is the newer one. So, Aaron, why don't you show us and tell us a little bit more about the first version that you released?
Sure. So to begin, I wanted to start as simple as possible. Eventually, we want to make this become a product, and we're still not finished. But this is where I started, no handle, and it was just as simple as possible. Hey, let's just have a linear rail, and there's different versions we could use of that. But that's just, hey, it goes up and down. It doesn't really require a lot of force typically to do this. But this is where I started. Even without this spring, it was just, can we just guide this thing straight up and down? The fundamental form of getting this in straight, we just need vertical, perpendicular motion. So this is where it started.
You only use your hand to move it up and down?
Yep.
Oh, look at that.
And then there's a constant force spring to say, hey, don't let it drop onto the table. I think that was even sort of iteration 1.5 was to add the constant force spring. But yep, it's just straight up and down.
Now, what was the next phase?
So then as we started saying, hey, we needed to have more force, because some of the bigger sizes do require quite a bit of force, as long as if you don't want to go too hot on temperature. These were just some of the earlier versions of just the head part. You can see this had another attachment here where we had a handle and there was a gas spring to assist this going up and down. But we really said, you know what, that's probably overkill. It's really not a heavy thing. You can grab it by hand and raise it up and down. So let's eliminate that part. This was a next version where you can kind of see it's blockier because we weren't trying to get the industrial design right. It was more just, hey, is this function and this general design going to work? And then the version you see now, all the way on the right, that has industrial design. So I didn't do the industrial design. I started with this blocky shape, and we've got a great industrial designer that made it look better. And then we still got another version to do to make this more manufacturable, but this is the one that we've been working with for quite a while now.
Aaron, so talk to us a little bit more about the inspiration behind designing this and your whole thought process behind it.
Sure. So I think it's pretty standard, right? Understanding the problem first. So when I walked in, this was an idea, hey, you know, we need a middle of the road solution. The owner of the company wanted something there. So first, to really understand what the problem was, rather than jumping to the solutions, which is always the natural tendency, maybe even worse if you're an engineer, was to say, hey, what really is the problem? And so I just took our standard solution, which was a soldering iron, and just practiced that, right? What's this really like, so I can have the hands-on experience myself rather than hearing word of mouth. So did it myself.
So it's almost like a detective mode. You want to get yourself in the shoes of the user?
Exactly.
Okay.
Yeah. Let's do this ourselves so the problems become really real, and especially the nuances. The nuances really matter and make a difference between a machine that works and a machine that you love to use.
So now Aaron's going to show us the requirements document, which is something key, as many of you know, when doing mechanical design engineering. So Aaron, why don't you walk us through the requirements document and what it is?
Sure. Maybe the really important part about this is knowing that it's iterative. So when I first started doing it by hand, I had a few requirements. But then as I learned more about competitive products and using it myself, more and more requirements came out. But that's helpful overall just because it knows what you're designing for. So the way that we do it here is overall on the left, it's kind of a hierarchy. What's your overall mission statement? That's installing heated heat set threaded inserts. And then the user needs, which are pretty basic, versatile. Here we say it's easy to use, safe and ergonomic, but it's really hard to quantify what that means and how you design for that.
So right now he's reading the second column.
You got it.
It may be a little small from people seeing, but just some requirements the user may have.
Yeah, and then we talk through the priorities of, here we say must have, could have, should have, or won't have. And then our design inputs are usually quantifiable and numbers, right? So this is exactly what sizes we're going to target and which sizes we're going to leave out, or how much stroke do you need, or how much throat do you need, how big of a part can you handle, things like that.
I'm smiling because wouldn't the world be such a simple place if we could all just communicate with each other with quantifiable inputs, like I need this amount by this time, and everyone would understand each other. But this is engineers translating these vague needs, right, into like tangible, quantifiable amounts.
That's right.
All right. What about these clarification notes on the right?
Well, these are things that we don't know yet. So for example, what materials do we want to target? And depending on which materials you want to target, that changes your temperature range of everything. And that changes things like, oh, can you use silicone or not in the holder that we showed earlier? And we want to have more space up and down, but we accomplish that by sliding the entire head assembly up and down on this. Right now it's an aluminum extrusion. So most of your motion is accomplished out here, and the final motion is accomplished here with the quill.
What is this back here, if you want to zoom in?
Yeah, that's just an adjustable handle that you can quick release. It's about a quarter turn. You can see that I just have the basic dimensions. So I did this early on. You'll see it later down in the feature tree. But it was just saying, hey, how much travel do I want to move? And I was using tape measures at my desk to get the rough ballpark, and how much force amplification do I want to get. So here you can see those dimensions of 150 millimeters versus, what's this one? 60 millimeters.
Summary: to get an idea of how a mechanism will work, it's not a bad idea to do some undefined sketches, give it a few constraints, play with the dimensions, see what looks about right, and then try to see if you can translate it in front of you with a tape measure to see if it would be comfortable, right?
Yeah, I'm usually against undefined sketches, but in the case here where you want some motion, you don't have to have any mates. If you do constrain it properly, you can make motion with just with a sketch.
Makes sense. Well, is there anything that I haven't asked you that I should have asked you?
Oh, that's a good question. Maybe one thing to think about on this is intellectual property. So threaded insert installers exist, but what makes this unique? And we're always checking ourselves. Yeah, we can design a product, but is it going to sell in the marketplace? That's still to be determined. We've done some consumer testing with it and things are looking good. We also have a provisional patent application, which is a way to really, when you can say patent pending on this now, and that's a way to make it so you don't have to write a full patent when it's not fully designed, but at the same time you get some protection and you get some earlier filing dates. So that's maybe something to think about too. Yeah, you can design something, but should you, can you, is it protected, etc.
And just to clarify, this is not legal advice.
No,
or
it's
legal.
not.
You're always gonna throw that out there.
Yeah, we have
Contact the lawyer. You know the routine. Well, Robinson, thank you so much for being on the show. We appreciate it.
You bet. Thank you.